transverse loading is a loading, for example, we've seen in our shear diagram. If this is a cantilever beam, taking, for example, a force, and for example, the force here, say, if this cantilever being used to hang up a weight, so the weight apply the force to the beam. So for example, if we pick a cross section here, then this weight will impose a loading which force equal to weight. So that means by equilibrium, here we have the using equilibrium equations, and in magnitude this equal to the weight. V is called the transverse loading, and this transverse loading, again, you can draw the shear diagram, and that means you can find the distribution of the transverse loading throughout the whole beam. And this transverse loading will induce one kind of the stress on this cross section, because this force you can see is parallel to this area. So this will induce the shear stress. Okay, and what is the magnitude and how to calculate the shear stress on this cross section? That is a topic in this chapter. So this will be our the last one, the last loading type. This will be the fourth one. Axial loading in chapter 2, and torsion in chapter 3, and bending in chapter 4, and this one transverse loading in chapter 6. And turn out this one will be the among the four. This will be the most challenging one among the four. Okay, but again, there's only one single equation in this chapter, and then apply the equation in the correct way for many conditions. By the way, here for this chapter, I'm going to take about 5 lecture hours today until. Let me look at my. These lectures will take 4 hours to complete. So that means by schedule we will complete these topics by Monday next week. Hopefully, I wish I can complete that one. And then by schedule we're supposed to have test 4 on Wednesday next week for this chapter. How many of you in fluid mechanics? Raise your hands. Majority. Okay, and you have a big test on next week as well, right? Friday, which day?
Yes,
Friday. So it wouldn't have any conflict to our test, right? I don't mind if I can reschedule the our test. Okay. If you wish, I don't know how many you wish to reschedule the test. So that means not be happening of the test on 2 tests on the same week, in the same week. Do you like it, or no?
Maybe can we see like how we progress through this?
Just pick progress like this.
Or if we kind of see how we progress through these chapters. Yeah, it's on that. You know what I mean? I haven't got it either day.
Here, I believe most people are here. If you like to stick with the original schedule, raise your hand. Wednesday next week. Okay, thank you. If you like to reschedule, for example, after your fluid mechanics test, raise your hand. Yes. Thank you. In this way, we stick onto the schedule. Okay? And then the test will be on Wednesday next week. And I will try to supply to you the many examples, and then to the homework, basically you can also exercise this. And now we're back to our lectures. again, our goal is to calculate the shin stress on the cross section, and how to calculate this one. And actually, yesterday I sent you the email asking you to preview our textbook certain pages, right? And then ask you to review. This is the solution for our questions in the chapter 4. And let me give you the quick overview of what was this problem. For this problem, basically is this. This is, for example, here I take the T shape of the cross sections, and simply I'm asking you, for example, to integrate the bending stress over this shaded area. And this shaded area, basically, we can pick any level, we can pick any size, and then we can calculate is this. For our bending stress, say this is a T shape. And this is a centroid, and this is a neutral axis. And for example, I pick this level, and which is arbitrary. And then from this level, I pick this shaded area, and on which we're going to integrate over the bending stress over this one. So we know that, for example, in this small strip, that position away from the neutral axis, which is, let me call it Y. And the bending stress is, the magnitude of the bending stress is my over I. Okay, and now we simply want to integrate this form over this area. So here you can see this amount. Let me call dy. So that means this is the area, basically, we integrate. Let me do this one carefully. So this is the magnitude of the bending stress. And multiply, for example, say, let me call this is the, say, T. Then this small strip, dA, will be equal to T times dy. So this represent is the small force on this small strip, and then we simply integrate from, for example, from the bottom to here, and from the bottom to here, for example, say the bottom here, for example, here could be whatever, and let me take this is the over shaded area. That means this is integration take over the shaded area. Okay, and then here we have the magnitude I that is independent of the position Y. So basically this one basically can be converted into this integration of Y squared of Y dy. Let me, since I picked the, that's okay. Will I be allow me to use the symbols here? For example, to make the simplicity, say without any too many writings. So for example, let me just take it as a dA. Okay, so basically dA is this area. Okay. So then the integrations will be equal to m. That is a constant, and I is a constant independent of y. So y dA. And this is the over the shaded area. And this one, again, we can use the our static. The information is this. If we know the centroid, this is the centroid of this. This is the, let me say, this is the centroid of the shaded area. And then the distance from the shaded area to the neutral axis, let me call it, is called the y bar star. Then this quantity basically equal to the shaded area multiplied with y bar star. Okay, this integration basically can be replaced by this multiplication. We simply multiply, take the whatever the area of the shaded, what area of the shaded shape, the region, multiply with the distance from the centroid, from its centroid to the neutral axis, simply is this one. So basically, the whole thing becomes this. Okay, what this means? I pick this one here. For example, here I have done something on my bar, so you can say I cut off something. So for example, if this bar is cantilevered to this end, and then right now if I apply the point loading to here, so basically right now for this case what I'm doing is this scenario. For example, here I apply the point loading, let me call it P, and say the whole length of this is called L. So basically that thing is here, I cantilever here and then apply loading, so that is like this, become like this. Okay, and then we can draw the bending, shear bending moment diagram first. So on reaction here, this is P, and the reaction bending here equal to PL. So the shear and bending moment diagram for this case is this. Will I be right?
Wouldn't the reaction go the other way for the moment?
Oh, the moment should be in this direction. Thank you. Okay, so this is the for the shear diagram. For the bending, that will be starting from here. So these are x, these are x. So the slope equal to this magnitude equal to minus p here. Okay, so the slope equal to minus p. So that is what we have done from the previous chapter. So that means the beam like this, and we have point loading to point down. So from this end, which is x equal to 0, to this end, x equal to L, that we can see the distribution of the bending on each cross section. The magnitude of the bending is different, right? That is the first point I want you to recognize. So the bending, distribution of the bending in this beam is not constant anymore, okay? And before, in chapter 4, we talk about the pure bending. The pure bending is the same. Now it's not anymore. So now I pick two places. The first one, let me pick, for example, say, in this cross section here. So basically here, let me, how about this? Let me just displace my plot. So what now, what I want is this, this is this beam. And then what I want to study is this portion. Okay, so this portion basically, in terms of view, will be like this. Can you see it? Okay, so which means right now I pick a, let me draw the two sections. These sections and these sections. And actually what I'm looking for precisely is this free bar diagram. And this free bar diagram, again, this one. This is a whole beam. This is the portion I'm looking for. Okay? On these portions, again,
I'm just wondering, so did you just kind of arbitrarily pick those points because that's what you had
yes,
drawn?
I arbitrarily, for demonstration, I arbitrarily pick the two sections.
Okay.
And then I'll arbitrarily pick this level. Okay, so basically the two sides, position here, arbitrary for illustrations. And the depth here, arbitrary for illustrations. Okay. And what now I want to do is to find out what is the distribution of the bending force on this area. So right now I pick is this block. And right now I want to try to integrate, try to find out is what is the total bending stress over this area, this small area, and also on the small area, which corresponding is this position. So right now, again, this side climb, we apply bending like this. And right now, I simply want to find out what is the total force here, here. What is the total force? What is the total force there? Okay? We can use this equation. So let me simplify this. Again, we can utilize this equation here. And for this case, the bending is like this. So let me draw the free bar diagram of this part to here. Let me enlarge. So the dashed line representing is the cross section on the two sides, okay? And this is the free bar diagram we pick, which means this part. Okay, so let me put into 3D. For example, let me put it into 3D. This will be looking like this. Okay. So right now this piece just like this. Okay? And then what I want is to repeat the calculation. This is the shaded area corresponding to this drawing. Let me show the entire cross section using the small dash. This is the entire cross section. Okay, so that is the entire cross section we dealing with. But okay, now what I want is, again, apply the same rule. So on this side, for this example, the bending is like this. So on the top portion is in, this is our neutral axis, right? Okay, and for this case, the bending is bent over like this. So upper portion above the neutral axis is under tension. So schematically, let me draw the, okay, so tension. So this is the bending stress on this side, like this, okay? So this is the bending stress. And say, for example, here, this side corresponding is corresponding to those positions. So let me highlight it here. So let me call this is point A. This is point B. So this corresponding, this position is XB, and this is XA. Corresponding the value, for example, this magnitude, say is this one, this magnitude here is MB will be equal to minus P times XB. And the magnitude here is, let me call it MA, and which is minus P times XA. Okay, here I just try to fix the magnitude of the bending here. So the bending stress at this side, this is B, this is A. So the integration, I want to calculate the total horizontal force here. I don't know how to say it, but here. Let me use this one. Okay, this is what we call the shaded area. Okay. So we want to calculate what is the total horizontal force on the shaded area at A and B. Okay, so here is our calculation. The reason why is this. At point A, that is corresponding to here, we plug into our formulas here. Formula is magnitude is M divided by I times start and A star. So let me call this the total force at A is equal to, let me draw the force here, the total force, that is the tension, so that is the tension here. Okay, so that is the bending stress. So here the total force, we put this formula. Again, the formula magnitude is taking this one. Again, everyone should familiar with this formula. I picked that template, so that is M, the magnitude of M at A, divided by I. The moment of inertia, what is I? The moment of inertia of what? What is this I? Think about that one. Let me turn off the light. In our formulations, what is this I? This I coming from here, coming from here. What is the I? I is equal to the total, the moment of inertia of the total cross section. About where? About the neutral axis. Okay, so keep that in mind. And then Y bar start. What is this one? For example, for this one, say if this is the centroid of the shaded area, and measure that distance to the neutral axis, this is our Y bar star. Okay, that is here. And then what is this A star? A star represents the shaded area. Let me say this is the shaded area. Okay. At B,